interesting about all these methods is that they are not fully understood, in the sense that a lot of the math underneath isn't properly developed, or maybe it has been developed in some corner of the application space, but not everywhere. So oftentimes it's much more of a discovery situation. You try something and see if it's going to work. Sometimes it works and sometimes it catastrophically fails. And from the failures, you get some sharp insight saying, oh, now I see what's going wrong. So that's the beauty of it. It's not boring. It's always, something always happens to bite you. So I think it's really, really cool. Okay, next. All right, so fine. So before Nick takes over, I just want to introduce the ExaSky team. So this is a 4-lab collaboration led out of Argonne. I'm the PI, and then there's also people from Los Alamos and Lawrence Berkeley, and Antigone, who's from Oak Ridge, helps us get our codes running on Crusher, and hopefully soon on Frontier. So Nick, please take it away.
Okay, hopefully I'm unmuted. Yep. So thanks, Salman. As Salman stated, I'm going to just briefly go over a couple of stochastic examples in HACC, although there's quite a lot one could talk about, and so I'll try to highlight the pieces as I go. Essentially, we should describe what the code actually does. So as Salman said, we're basically simulating large-scale structure formation of the universe. And the idea is that we need to do this in very large cosmological volumes so that we can produce, for example, synthetic catalogs or mock realizations of the sky. So you can take these mock realizations of the sky and you can hand them over to ground and space-based observatories, and you can help them control their systematics as well as their analysis pipelines. And so it's really important that we run these really large simulations, which requires large-scale control accuracy multiphysics simulations with a very large dynamic range. And we do this with a code called HACC, which stands for Hardware Hybrid Accelerated Cosmology Code. And essentially, I just like to point out, I'm not going to go into too many details about the code itself, but its design approach is what we typically call an MPI plus X approach, where there's two fundamental pieces. The first is a spectral particle mesh solver, which essentially lives in FFT world. So you're just taking a bunch of FFTs, and it's completely communication dominant, but was written to be scalable to millions of ranks and process grids of sizes 15,000 cubed and larger. And so this solver, which is written in MPI, essentially has over 90% parallel efficiency and is how the code perfectly weak scales on whatever machine we run on, just because it's portable since it's written in MPI, which every machine will support. And so you have that base spectral solver, which then on top of that, you then have a bunch of short range force kernels. And these short range force kernels are actually where the compute power is. And so they're all very computationally intensive. And by design, the hybrid solver made it so that these short range solvers are node local. So there's no communication. And then this is where you really use the flops of a machine. And that's the X part, where we actually will rewrite these short range force kernels in whatever language the machine, domain specific language the machine might be in. So that could be OpenMP, CUDA, OpenCL, SYCL, etc. assembly. And it's because of this design that we're able to run extreme scale simulations on all modern computing hardware. So for example, the image on the left is one rank from a trillion particle run that we run on Summit. And on the right, which I'll actually blow up, is a run we've run on a multi-core machine. And so I'm just showing you an image of one of these simulations to give you an idea of the very large dynamic range of these simulations. As you can see, the entire box volume is something like 3.5 gigaparsecs. And as you progressively zoom in on one of these simulations, you see you just get more and more structure formation, where it turns out typically in our simulations, we have 1,000,000 to 1 dynamic range. And this final circle here is roughly the volume one rank would be evolving in this entire simulation. And so you need a lot of ranks, which are all working together to simulate a massive volume to produce the observables we're interested in. And so hopefully that gives you a very brief understanding of what the code is. And I think it's important that we at least understand what the physics are going on behind it. So a majority of the universe, the majority of the matter in the universe is what's called dark matter. And for the most part, we think it basically only feels gravitational forces. And so as a fluid, it'll obey the Blasov-Poisson equation, which for those of you who are plasma physicists will recognize this equation instantly. And essentially it's a 6-dimensional PDE plus 1 dimension for time. So if you were to naively solve this on a grid, it would scale like n to the 7th, which is not something tractable for a problem that has 1,000,000 to 1 dynamic range. And so what's typically done is you actually sample your density field F with particles and you solve an n-body problem. So essentially you're integrating out the momentum contribution of the density function And for each of these particles, all you have to do is calculate the gravitational potential following the Poisson equation. You move the particles and you rinse and repeat. So it's an n-body solver. And while we're here talking about stochastic methods, Salman highlighted that there's a whole lot of elements of stochastic theory that just come into the fact that we're doing an n-body solver, how the ensemble is giving you the solution you want, whereas the actual variability of individual particle trajectories is actually not as important. And so that's a whole other talk that would be very interesting to look at. But in this case, we'll just take for granted that we have an n-body solver with particles that feel gravitational forces. On top of that, the universe isn't just feeling gravity. You also have normal atoms, which feel gas forces. So at minimum, you need to also model an ideal fluid, which would be the simple Eulerian equations I've written here in Lagrangian form. So to first order, what you have to do is couple the Eulerian equations to the Poisson equation, and that it will at minimum be tracking sort of what the gas and the dark matter is doing. So in practice, what that means is you have particles sampling dark matter, which only feels gravity, and you have particles representing gas that feel gravity coupled to hydrodynamic equations, where the hydrodynamic solver that we use is typically an SPH solver. So we take a Lagrangian particle approach for that as well. So yeah, HACC has these two major components. And then on top of that, the remaining physics comes from astrophysical effects, which I'm about to talk about in the next slide. And that's actually where the stochastic methods come in. So I'm going to talk about two very small applications of stochastic methods in HACC. The first is in our initial condition generation, and the second is in our subgrid modeling, which has to do with these extra astrophysical effects I was talking about. So it turns out the universe is basically a sampling from a random Gaussian field to the best that we can tell, which essentially means when you start a realization of the universe, every particle needs to sample from a random white noise field. And so immediately you run into a reproducibility problem, where if I give you a fixed number of particles and let's say a fixed realization or random number seed, I need to make sure that I'm deterministically having the same initial condition no matter how many ranks or threads I have. So that's a very simple problem that all of us in our applications have solved in one way or another. And the way we approach that is with CBRNGs, which I'll talk about in the next slide. But that's one problem. So you have the initial conditions where you need to sample a white noise field. The second is actually a much more intensive problem, which is called subgrid modeling. So not only are we modeling dark matter and hydrodynamic effects, we also have to stochastically model star formation, galactic winds, active galactic nuclei, et cetera, which are astrophysical processes happening at much smaller scales than we can resolve and need to come in as source terms in our equations. So I give a very simple toy model example of what this means. So I have a very simple equation that says that the gas in my simulation, given some certain criterion, needs to convert into stars at this rate over some time scale t. And so I could solve this equation analytically simply with just an exponential function, but the mass of my gas particles in the simulation is much larger than the time scale of conversion. So you'll get mixed states where I'll have gas particles that will slowly become stars and therefore couple the stars to the gas. And unfortunately, physically, this doesn't make much sense. We want our star particles to only feel gravity, and we want our gas particles to feel both gravity and hydrodynamics. And so deterministically or analytically solving these types of ODEs is not actually what we want to do. And so what's done typically in practice is you actually solve these ODEs stochastically, where you take a random probability that a particle of mass m converts to a particle of star of mass m star with this probability. And then you just do random number sampling every time step to see if this actually occurs. Where the ensemble will again follow this ODE, but now it's no longer coupled because you're either a full star particle or a full gas particle. So this is just a long-winded way of saying that to do these sub-resolution modeling, we have to solve a lot of ODEs for each individual particle, and we typically solve those ODEs stochastically to avoid a lot of these coupling issues that you have if you solve them deterministically. Okay, so that's initial conditions and subgrid modeling. How do we solve this initial condition deterministic problem? Well, we use what are called CBRNGs. So typically a random number generator is a sequential state transformation. It means you take a seed that produces a state, you take that state and you put it back in the random number generator and it gives you another state. And so you get a dependency chain of random numbers, which unfortunately is actually not naively parallel. CBRNGs, on the other hand, have no state. Where essentially given an arbitrary count and key, where a key is typically what you would think of as a seed, the CBRNG gives you a deterministic random number. And so this is quite nice because if, for example, I have n particles in a simulation and I identify them uniquely by, let's say, an index, so a number between 0 and n, and I call that the count, Now just the particle and its ID will determine a deterministic random number, which will then solve my initial condition issue I had, right? So it doesn't matter how many threads I have or how many ranks I'm on, because that particle has a unique count and a unique key, that will give it a unique random number, and I can sample that white noise field without worrying about robust issues at scale. So that's sort of why CBRNGs are very useful. Different keys, of course, gives you different realizations, as does most random number generators. And it's obvious how to get a sequence of random numbers, because if my particle is at index 0, then if I make my count 0, n, 2n, 3n, 4n, I'll get a sequence of random numbers that are unique to that particle. And if my index was 1, then 1, 2n plus 1, 3n plus 1, et cetera, would give me another unique sequence. So CBRNGs are really useful for particle methods just because you get a very deterministic sequence of random numbers that doesn't care about threading or anything like that. And my two final points about this are just that these methods are typically very fast and are the same speed, if not faster, than normal random number generators. And you can use the random 123 library as an example for many implementations of this. And so I just have two quick final slides. One, which is that we solved the reproducibility problem for the initial conditions with CBRNGs. But for subgrid models, it's actually even more complicated. Essentially, long story short, our simulations have evolved a fixed domain. And that domain, like I said, you have to solve short-range forces for each individual particle. And the problem is that if I have particles on the edge of my rank domain, they're going to want to see particles from my neighboring ranks. And so I either have to communicate with my neighboring ranks continuously for each time step to make sure that I have all the particles on the boundaries evolved correctly, or you can do what's called overloading, where you extend your rank domain such that you have overlapping particles with your neighbors, such that you don't have to do communication. And this is very nice because now your ranks become independent and they don't have to worry about, they can do all their local forces on node. The problem, of course, is if I do this, these red particles, which I'm now replicating from my ranks on my current node, I now want them solved deterministically on all nodes, no matter how many nodes I have, and no matter how many threads I have. So again, it sounds like, yes, we should probably use the CBRNGs to take these probabilities. But the problem is that the probability of that I listed in this very simple toy example depends on the time step of my sim, also might vary on all of the ranks. And so it turns out the simplest way of solving this issue is in all of our subgrid models in our simulation, we actually evolve the stochastic integrators at a much finer time scale than the actual simulation integrator, so that they're all on a fixed random number sequence. And then that solves the reproducibility issue, because now the time step for elements thrown out, and I just need a sequence of random numbers per particle per rank. And so long story short, that means that to do this problem with subgrid stochastic integration, we basically need to take many, many CBRNGs, because we need to integrate an equation at a much smaller time scale than the simulation is. And that leads me to my final slide, which is that we do this on the GPU quite efficiently. We actually use CBRNGs following the squares method, which is actually what John talked about earlier. This is the Van Neumann middle square random number generator. It's basically this, but in the CBRNG form. So you can see the instructions are quite simple for a GPU to understand. This is how you get a 32-bit integer, and this is how you get a 64-bit integer. And essentially, with such an efficient random number generator, and because it doesn't care about threading, like I said, it's embarrassingly parallel, we can now hammer away these stochastic equations on the GPU. And it turns out they're much less dominant in our time to solution than any other force calculation, like, for example, hydrodynamic forces or gravity forces, because those solvers actually require your particle neighbors, whereas the stochastic integrators only require your particle state and randomly sampling a bunch of random numbers in sequence. So anyway, I just want to conclude by saying these CBRNGs are very useful. You can run many of them in parallel at a time. And often people talk about issues with branching. And what's kind of nice about solving stochastic ODEs in the way I've described them is you can actually sort your particles by this probability. And therefore, if a bunch of particles have a low probability of converting, for example, in that example, then they won't be branching because they'll all be following the same logic. And so, yeah, with that, I'll take any questions. I'm sure we're running late, but that sounds good.
Yeah, thank you, Nick. That was great. And Salmon, thank you as well. Yeah, we'll open up to questions. I guess I just wanted to start off. So when you're sampling your initial conditions for your particles, do you have any sort of k-dimensionality issues where sometimes with LCGs, if you are sampling in 3 dimensions or 7 dimensions, you start to get these planes that show up? Since you're using middle square, is that like immune to that, or do you have some other?
It's not a problem specifically just because the dimensionality gets completely projected to 1D, right? Once you have all these particles. And for running a trillion particles, I think about how many numbers I can store in a 64-bit integer. It turns out I get hundreds of thousands of numbers, which is enough for these simulations. And then if it turns out I run out of numbers, I just CBRNGs allow me to use the same seeds, but then sort of loop over again. So I can avoid a lot of the dimensionality issues that Monte Carlo codes have, just because the problem in the way the problem is posed.
Gotcha. Yeah, that's really cool. You're using middle square. I had no idea that that was widely used. That's really cool. Are there any other questions? All right. Well, we can always come back if we have time at the end to ask more questions, but I'll pass it off to Yi.
Okay, let me start my sharing. Okay.
Looks good.
Yeah. So I'm Miro from Argonne National Lab. So today I will talk about the hierarchical parallelism in QMCPACK. So the design of the parallelism is tightly coupled to the nature of stochastic behavior of execution. So fit this session very well. So the work is done with Peter Doak from Oak Ridge and Paul Kent also from Oak Ridge. Paul Kent is the ECPPI. So QMCPACK is a open source package for using implementing the quantum Monte Carlo algorithm. Quantum Monte Carlo, you can decouple the name as quantum and Monte Carlo. So quantum is because it's related to doing simulation of electronic structure calculation problems. So basically we solve the Schrodinger equation. And Monte Carlo, yes, the solving method is via Monte Carlo with sampling. The code is with basically C, C++, and using Mpi plus X, like every other program nowadays. So I still need to emphasize that Monte Carlo and quantum, these brings the concurrency in the code that used for parallelism. It also brings challenge. I think most people are not in this quantum Monte Carlo field, so maybe I can give you some ideas how the code actually runs. So it starts with a bunch of electronic configurations. So think about a simulation. You have a box of electrons, then you do random walking, and then you have many replicas. So they form a population. As time moves, so each configuration we evolve it over time. We call it Walker. So at each step, you propose some new electron positions. You compute certain quantities. You make a decision whether it's accepted or rejected, this move. Then you calculate a bunch of other things, assign weight. Then you do, based on the weight, the Walker, some Walker has light weight, some Walker has heavier weight, represented in statistics. So you do a load balance, killing all the small weight ones and duplicate the large weight ones, making sure the population is stable. Basically what we are doing that. So now let's go to the parallelism. As I mentioned, we have a population of walkers, this level, but this naturally brings the concurrency. I call it boring part because usually when you talk to people about Monte Carlo, they'll say, oh, you are embarrassed parallel. That's true to some degree, because if we look at the computation per walker at each step, it's actually a fixed wall time. So each walker is doing the same amount of workload. That's why it can be easily parallelized. So this walker parallelism has been used over MPI and OpenMP threads and always give you almost perfect loading balance. So it's very efficient on modern computers, supercomputers with massive cores, massive ranks. Yes. So, however, if we go down deep into the algorithms, we look at what happens within one step of calculation of a worker. So at this level, there's no synchronization needed with other threads, with other worker, basically. It's all by the worker itself. So within step, we have to propose a move for each electron, and then each electron will be moved, the move will be proposed once. So the total computation cost is n cube. Within each single electron move, there are some computation that you propose move and compute wave function ratios. The cost is n to the first once or to the second. The next step will be you do accept or reject. When you do accept, you compute certain quantity of the wave function, which is n cube, right? Which actually is the leading scaling algorithmic complexity. That leading term is from this accept. However, if the worker has a reject, it has nothing to do, so it's zero cost. This means that at a certain point of time, your workers are not doing the same work. So some workers may be doing these heavy updates due to the accept, but some workers may move forward doing another thing. That's why those small tasks caused a problem that workers are all out of sync. They are not in lockstep. So what we typically solve on the CPU is all these tasks of a given worker are just serialized within a CPU thread. So for a given worker at a given single electron move step, it may accept, may reject, but over time, when all the electrons these moves have been proposed and handled once, the ups and downs, the cost evens out. That's why, if you remember the previous slides, I said, after one step, the cost, kind of the timing becomes the same for each worker. So on the right side, you could see that there's workers. This is a parallel loop, and under it, there's the sequential loop over all those single electron moves. So still beneath it, we do a bunch of calculation around the pair interactions or evaluating orbitals. They are still very, very good. They can utilize the compute power of modern CPUs, which have a very wide SIMD unit. So this was kind of okay for a very long time. However, it becomes a challenge for GPUs. So still, if you look at the CPU driver, that GPU kernels cannot cross the border of this sequential loop. So it kind of be restricted at the bottom level. However, at this level, there are so little compute because, as I said, the compute load is only designed for a CPU core with some SIMD unit. But GPU is 20 times of that. So what we can do is by interchange the loop of the sequential single electron move loop, move it out and take the worker loop to the inner, then fuse this looper with the lowest concurrency and making sure we have a large enough kernel for each GPU computation dispatch. So this scheme was used in the QMCPACK legacy CUDA driver, which has been working well for almost a decade. Just to emphasize the character of doing this loop interchange, now because the single electron move is handled at the outside, all the workers would have to execute in lockstep. So think about, they do lockstep means they do the same operation. So you execute and accept. That means only part of the worker will do the computation. The rest part will be just either you remove it from the list of all the workers. So GPU kernel, since you know that you can control the blocks, you just reduce the blocks. So even for the GPU, you will see that the compute will fluctuate a bit. So this classical design of QMC drivers just bring us tons of troubles. the CPU classic driver doesn't work friendly for GPU. And the nice part, as I said, is asynchronous between workers. The legacy CUDA implementation is very good for GPU, but you can't force that way of compute back to the CPU because you just leave CPU cores idle. So there's these disadvantages. And also because of code divergence, the underlying APIs diverge over time, and we have a lot of feature gaps in the code. So user experience will kind of severely restricted by this classic driver designs. So if you look at this picture, it's kind of explaining you. So we want every scenario in the dimension of number of electrons from small to large, number of workers, small to large, all work very efficiently. But those drivers kind of just worked in a small area, right? So it's users has to pay for making a selection, but usually for users, they get on a HPC. They don't have any choices. So that's our design goal, to adjust the kind of design in the code to make sure we cover a large range of parameter space for the electron and workers. So the idea is to introduce a new concept, basically introduce a new layer. So the worker, all the workers in a population now will be subdivided into crowds. So this is not a physics concept, it is more of compute, how we design the code, the concept inside the code, how we dispatch the workload. So if you look at the batch driver compared to the previous classic driver, like the CUDA driver, you will see that the levels changed from 3 levels to 4 levels. So the worker loop becomes 2 loops. One is the crowd loop, one is the workers within the crowd loop. So by doing that, this now can be easily matched to the both CPU and GPU hardwares. Think about when you are doing CPUs, you add the third loop over workers in a crowd, you just set it size 1, so that you don't get any penalty. And then on the GPUs, if you want the exact legacy CUDA implementation behavior, you can set the first loop as size 1. However, in modern computer, HPC nodes, it's hybrid. So we have a bunch of cores, we have very powerful GPUs. So in the modern node architecture, we actually recommend users at the loop 1 to utilize, just put the crowd as the number of OpenMC threads as the cores, making sure that all those crowds have work and kind of busily enqueue tasks into the GPU and keep the GPU busy. So by doing this change, we have a new driver, fully CPU GPU agnostic, because all the computation, the difference between CPU and GPU will be hide at the loop 4, the 4th loop level. Those are kind of taken away from top designs, top hierarchy of the code. So with this, and also because they're agnostic to CPU, GPU, you can do fallbacks. If features not implemented in GPU, you put it back on the CPU. So by doing this, it's actually, we successfully changed the design of the code and make the CPU, GPU portability and possible, and also performance can be optimized to the best based on the hardware. So just give a bit more ideas how things actually work. So as I said, you have, think about now you have 8 workers in the population, you subdivide them into 2 crowds, each have 4 workers. So you see the 4 squares. So these 4 squares. So if 3 workers accept it does some work, and there's 1 worker gets rejected, so it doesn't do any workload. So you have those compute tasks from each crowd, which individually live on threads. Then they will dispatch those compute to the GPUs, or maybe just use the CPU if they're lightweight. So those tasks now kind of being dispatched to the thread, to the GPU, and GPU gets extremely busy. So that's the goal of using GPU. So CPU needs to enqueue enough work, keep the GPU busy. in this design, we also allow CPU to do some work if necessary. So this maps perfect with the modern node architecture. So that's what we achieved. We actually implement the underlying GPU with OpenMP offload, and we also have the still some cuBLAS those vendor calls. But anyway, this picture is to show you that compared to our on the GPU, compared to our Lexi implementation, Lexi CUDA implementation, which is set as reference 1.0. So the new design with new implementation actually gets matching performance. Some scenarios up, some are better. And the largest problem, we even change algorithms and can be significantly better. So all this just works well when we have a good design that amortize the challenges from the Monte Carlo, the stochastic nature. So just a brief summary. By using crowd, we expand the two-level parallelism into 3 so that we can flexibly kind of move the sequential loop in and out based on the hardware. With this added flexibility, the unified QMC drivers now can maximize their performance for both CPU and GPU. So yeah, so as I said, this is perfect for GPU for modern node architectures. So every piece of silicon within the node architecture be fully utilized. So hopefully this gives some ideas for people who struggle with the Monte Carlo aspect, which just the divergence kill performance on GPU. So this is our way to solve the problem.
Great, thank you so much, Yi. That was very great. I'll open it up now for questions. I had one just on slide 14 there. You see kind of an explosion of speed out of your largest test case where your new driver or your new OpenMP version is running a factor of three times faster than the old CUDA version. So what all kind of is responsible for that? What happens that's magic at that kind of problem size?
Yeah, so this largest problem size is unique. It's a challenge because at this point you actually don't have many workers left because QMCPACK. Sorry, I need to explain. This is the number of atoms. Basically, you can think about the scale of the number of electrons. The algorithm itself is n cubed. So at this problem size, you are stretching at the limit of low worker count, very large compute per worker. So somehow you wanted to adjust the algorithm. Adjust algorithm to efficiently use the device and also to work around the memory limitation at this limit. So that's why we have special algorithms to deal with this. One is we do actually, at this limit, it's not best to put everything on the GPU. So certain workload becomes beneficial. Just do it on the CPU. On the other hand, the heavy jam, those things must be executed on the GPU. And we did a bit of algorithmic adjustment to make sure the jam kind of taking majority of the time. So that's perfect for GPU. That's why compared to the old algorithm, it's significantly better at this problem size. In addition, as I mentioned, that we made kind of high level agnostic. So then at a low level, specialize an algorithm just like stick into a new class and that's it. It becomes very easy. So the design enable us to add additional specialization for the tailored algorithm for specific needs. That's why you see this particular jump. All the smaller problem sizes, we try to get closer to the legacy CUDA because get close to the legacy CUDA implementation because we know that already works. So there's no reason to change it because it's already working that way. So we fall kind of the dispatch pattern in the new design fall back to the old legacy CUDA design.
Gotcha, where you basically have that outer, the number of crowds is just being one.
Yeah, crowd being one, we do gain something actually. Like on Summit, we have like 7 threads, right? We could gain a bit with adding more crowds. But we know that one crowd is a kind of reference, right? We need to match that performance. We know that that works on with the legacy cooldown.
Gotcha. Are there any other questions? All right. Well, thank you, Yi. I'll pass it off. I guess I'm the next speaker, so I'll pass it to myself. All right. Does everyone see my screen?
Yes.
Yes.
All right, thanks. Sounds good. All right. So for my section of the talk here, I'll be talking about work we've been doing on the OpenMC Monte Carlo transport code and getting it ready for exascale. So this goes beyond just kind of a rote, line for line porting effort, similar to as he was just talking about, that you really have to kind of reevaluate the fundamental algorithms to make them, to get things to make sense in the context of GPUs and of harder problems that you're trying to solve. Monte Carlo particle transport. It's basically we're taking a bunch of what we're trying to, in the context we're doing for our ECP challenge problem, we're simulating nuclear reactors. And so we're trying to figure out where neutrons are within that reactor. So they're born from fissions, they travel, they scatter around, and then they're either absorbed or they cause a new fission or escape. And so we want to know the locations of all those. And we do so not by solving a PDE deterministically, but by just trying out many particles and writing down what happens after each one. And so this ends up being a very, very high fidelity method and very general purpose. It's not tailored to some specific, sub problem space. You can use it for really a ton of different types of reactors and different sorts of problems. So it's very useful in general. The downside is that it's very expensive to do. And the stochastic nature of the problem creates a lot of challenges in order to do this efficiently on computers. And so generally this is, if we wanted to write out the PDE that this particle method is solving for, we're conserving over angular flux. So it's got a couple of different dependencies, space, angle, and energy. And then we can write out this Boltzmann steady state neutron transport equation. And basically it's just a balance equation across streaming. So as particles move from one control volume to another, an absorption when they're absorbed inside that control volume, and then also scattering. So if they change from direction or energy, what's coming into that control space, and then also fission. So particles that have collided, created fissions in that space, and then are generating new particles. And so there's a wide variety of ways of solving this. So on the left, there's the kind of stochastic methods, so Monte Carlo and random ray method. Monte Carlo, though, is the only one that really has the fewest possible assumptions and treats everything that with continuous treatment that it can. Whereas there's many other deterministic methods, ones I haven't even listed here, where you're discretizing many things. And so OpenMC is a specific application in this field, and it's part of the XSMR project. It's an interesting application because it's open source. It was started maybe 10 or 15 years ago by Paul Romano, and it has a wide variety of contributors. We have a lot of grad students that work on it that contribute some new piece of physics or new capability, and maybe they've only coded in Python or something before. So we don't just have expert ninja level developers. We have kind of a mix. But before XSMR, we were just a C++ code with MPI plus OpenMP threading parallelism. And then for XSMR, we've not only just ported it to a GPU model, OpenMP offloading, but also tackled many of the algorithmic challenges that face us in the context of GPU. So why is this so attractive though? Why is Monte Carlo so attractive? It's thought of as a gold standard. It's so high fidelity. And deterministic methods, while you can design reactors with them, they end up being, you have to apply a million little tiny correction factors, and that blows up the complexity of your code. blows up the number of assumptions you have to make, and it means you're not going to be able to apply that code to other different sorts of problems. So you end up with a very, very narrow design space. And if if you've designed some traditional reactor that exists and someone else has a new idea for a new reactor, you have to generate new software. It also makes it very hard for regulators to verify that a code is correct, that a calculation is correct, and so it creates many issues. Whereas if you can use Monte Carlo, it's very easy for a regulator or anyone to validate that, because the code is relatively simple. It's really just following the physics. We're not having to defend a bunch of discretizations or understand those. And so it's very attractive to that end if you can solve the computational problems that make it expensive and hard to run efficiently on computers. So why is Monte Carlo so hard for HPC? There's sort of two fundamental problems. There's many challenges that pop up, but the two biggest ones are, it's just a branchy process. It's there's not really a lot of natural SIMDization. If you're parallelizing over particles, all the particles are doing different things at each step. Some are scattering, some are absorbing. There's large regions of that would have to be blocked out if you're doing SIMD or something like that. So there's just not a lot of natural vectorization that happens. And then the second issue, which is just as bad, is that the driving data that supports the statistical sampling in the code is something that's known as cross-section data. And so you can see here like the probability of an interaction happening, which is known as the cross-section, and is totally dependent on the energy, the speed the neutron is traveling at. And so you see these wild resonances that span over 12 orders of magnitude in energy and 6 or 7 orders of magnitude in probability. And so you have to have like a really big giant table, and you have to do all these reads into there, and different particles are at different energies, so they're hitting different parts of these tables, and so there's like almost no memory locality either between particles. So this is kind of a recipe for challenge. You're definitely not going to get a huge amount of floating points. You're certainly not going to be a flop bound code, but even if you're just memory bound, you're going to have a really low cache efficiency, really low memory locality, and so that makes for a lot of challenges. Okay, and then so what kind of solutions do we have for that first branchy problem on GPU? On CPU, it's not so much of a problem because it's fine if different codes or if different threads are just doing their own thing. CPU threads can be independent. You can give up on trying to vectorize, but at least the threads themselves are independent. And that's what we call history-based parallelism, where each CPU thread processes a particle birth to death in a serial manner. So you have one big loop, outer loop over particle histories, and then within there it's serial, and each thread processes that task. And that, if you translated that to GPU, it would just be one giant monolithic kernel, where basically you have 40,000 lines of code that are just, that's your one GPU kernel. And that's not great for many reasons on GPU. The branchiness is bad, and also it's very hard for compilers to do a good job on that on GPU. You end up with a lot of register pressure, typically see a lot of register spillings, and we'll see that just empirically it doesn't end up with good performance. And so another idea that came up in the sort of late 80s with the vector computers was to kind of do a kernel splitting method and to flip the order of parallelism such that we can reduce thread divergence. So instead of having one monolithic kernel, we can have many small ones. And so just to give you a sense of, at a high level, what the traditional history-based method looks like, you kind of just have, this high level loop over particles, and then a serial loop within that over histories. And then if we try that on GPU, we end up with really bad performance. So we actually have that ability in OpenMC to run in history-based mode on GPU, and we end up really decaying. So just even compared to like a nice dual socket node, we're maybe only getting 20 or 10 or 20 cores of performance. So this is really, our accelerator is more of a decelerator in this case. So it's really a non-starter. This idea of kernel splitting, though, to move to an event-based model, if we do this, we see that if we kind of flip the order of loops in a manner somewhat similar to what Yi was talking about, where you kind of flip the loop ordering, we ended up with then sort of a serial outer loop, but then many parallel, a couple of parallel inner loops where there is an opportunity for some vectorization. And since all the particles here in each loop are doing the same task, there is possibility, even if the task has a little bit of branching in it, at least there's not, the branching happens at a finer scale. And so we can have some opportunity for SIMD efficiency. That's not a new idea, but when we tried it out in OpenMC, we had some great success. And the other really cool thing about the event-based model is it allows you to introduce some other cool optimizations. So something that you really can't do in history-based, but with event-based, you can now sort the particles. So you can sort them by space and energy, or by material and energy, such that now adjacent particles in a work loop here, like the cross-section lookup loop, now can be at the same energy. So remember, we had that giant cross-section graph. Well, now instead of hitting random spots, adjacent threads can hit the same spot, and that can have some really nice effects we'll look at. So overall, switching from history-based to event-based results in massive speedups. There's a few other optimizations that are included in these results here, but we go from losing significant performance by going to GPU to getting a massive speedup. So about 4x out of one GPU compared to a powerful dual socket CPU node. So that's very nice. And you can see that it wasn't just something that we missed in originally envisioning the algorithm. Event-based doesn't work very well on CPU. You have to introduce some queuing. You have to be loading and storing all this particle data. So it ends up that it's a net loss on CPU. And it is just the way the algorithms, which algorithms are most effective, switches between CPU and GPU. Okay, and something that pops up also in terms of going from CPU to GPU is issues with our random number generation and making them reproducible. So just the generator reuse is not a standard LCG. It's something called PCG, which is a tweak on a standard LCG. And we can get away with this. LCGs are known for having weak k-dimensionality, meaning that if you sample a bunch of, say if you're sampling 3D points or something, you can end up with these weird planes that show up, or 7D or 10D. And we don't have that because we're using our samples in a lot of different ways. We're sampling, how far they're going to travel, which sort of event is going to or which sort of collision is going to happen, the angle. So we use our generation in so many different ways that we're not really subject to these k-dimensionality issues. So we can get by with a very simple generator. We don't need something heavy like Mersenne twistor or something that guarantees 600-way k-dimensionality or something. And we use PCG just because it's a slight improvement. It's basically the same as an LCG, but it's a slight improvement in that it permutes the bits in there. LCGs tend to have stronger randomness in their higher order bits and weaker randomness in their low order bits, just as an artifact of the method. But PCG allows you to kind of mix up those bits in a stochastic manner that just slightly improves things. So we like that. And it's, as you can see, similar to the generator Nick showed, it's also very simple. It's just a couple of instructions. It's not a really heavyweight thing. And so it looks very, very, very simple, like an LCG, just with a few extra bit shift instructions. So it doesn't introduce a lot of speed or performance issues for us. And traditionally in CPU land, we had just each thread was storing its own random number generator stream. And that was fine. It would just get reinitialized each time based on a unique particle ID. So similar to what Nick was talking about, we have one global seed that sets the randomness for the whole simulation, and then we can fast forward to a specific point in that stream using a logarithmic fast forwarding algorithm. And that works great on CPU overall. But in event-based mode on GPU, we end up with a couple challenges. So in history-based mode, it's fine because each thread is going to serially process each particle from birth to death. But you can see here in event-based mode, we have all these different parallel loops, so we have no idea which particle is going to be handling which thread is going to be handling which particle. So if the threads own the random number stream, then we're stuck with a very random output that we can't reproduce. So the fix there is relatively simple on GPU. We just make sure that each particle object has its own random number state. So that's a very easy fix. What was slightly more difficult that we found is that we don't get reproducibility because the order that things happen is different with event-based mode, just based on which of these tasks happens to complete first, and gets pushed back to like a specific kind of a global array that's sitting in our simulation. And so with event-based mode, we can end up with like different things happening first, which means that on the next iteration, when we're sampling from that pool, we end up with different samples. And so we lose reproducibility there. So it turns out there's an easy way of doing this. Basically, whenever you have a fission site that gets generated, that's what you're going to sample. You tag it with the parent ID, and then also the parent keeps track of how many progeny it's had. And you can also do a very efficient sort with that. So overall, all these issues were really easy to overcome for us, or they had solutions for them. And so the net result is that with OpenMC, it doesn't matter if we're running on GPU, CPU, anything, we can get the same results. They're reproducible, at least outside of any small changes in, intrinsic math functions or something. But in general, they're reproducible. So that's been really positive. Makes our debugging and testing integration all a lot easier. So the next thing I'll talk about is solutions for accessing this cross-section lookup data. And so if we recall, I was talking about this, we have this cross-section data that spans all these different orders of magnitude and is a pain to access. On CPU, we actually had this legacy optimization that creates a cache that once you've done this expensive lookup into there, you actually store that data and you can reuse it in the future. And that can be beneficial just because then you don't have to do that expensive lookup again. And it ends up being quite a significant optimization, about 25 or maybe 50% speed up on CPU to do that. But what does it look like on GPU? Well, we found that here's our lookups. Like we have all these particles, and they're all looking up random data randomly from memory. And when we add in the cache, the stores, yes, it's also very chaotic as we store it. But then theoretically, if you're going to read from there again, it can save some time. And on GPU, remember we talked about with event-based mode, we can also sort our lookups before we do them. And in this case, now instead of accessing all these random locations, we can basically all threads in a block, not all threads in the entire simulation, but all threads in a block in a work group are basically loading from the same location, or very nearly the same location. And that's amazing because now we're, instead of having to load many different cache lines from all over the place, we're just loading like 1 or 2 cache lines. So all of those loads become shared, and our loading scheme becomes much more cleaned up. However, the loading bandwidth is great, but then storing to this cache we found on GPU was still really expensive, and sorting stuff just by itself didn't really get us much speed up. So the solution was, well, we just get rid of the cache, and we can do multiple loads now with event-based mode. And it turns out that even if we have to, instead of reusing a cache, even if we just do the full lookups again, we end up being much faster. And that's just because we're able to get by with unique cross-section data, or instead of having unique data that we're loading per thread, it's like just one set of data per block, and that ends up being a massive win. So you can see that overall that improved our simulation performance by changing this lookup pattern by about a factor of 2x overall on the simulation speed, and even more just for that kernel. It was more like a factor of 4 or 5. So cleaning up our kernel was a big thing, and that stemmed from moving to a GPU model and then removing some CPU optimizations. So rethinking things for GPU to make sure everything from CPU made sense. So where we're at now, just as a check-in in terms of performance, we did choose OpenMP, and that has allowed us to run in a portable manner across a variety of GPUs. We can also run on Intel as well. I just can't show those results right now because they're under NDA. But on AMD and NVIDIA, we're getting speed ups compared to a CPU. On NVIDIA in particular, we're getting really great performance. AMD is less impressive, given that the MI250X, for instance, here has about twice the theoretical bandwidth as the NVIDIA A100, but it's getting about the same performance. So we think there's some deficiency there. Maybe as compilers mature, we'll see some more speed up. Maybe there's some more optimization work we can do there. But at least where we're at right now, we're not running quite as fast on AMD as we'd like. But overall, OpenMP is running well. We don't think we're losing performance just due to OpenMP. So just a few last takeaways. fast supercomputers are making Monte Carlo more attractive and practical for routine simulation and engineering work, just because it's a very general method that can be applied to give very high fidelity solutions to like a huge problem space. And it's very easy to use and very easy to validate. But there's many issues stemming from Monte Carlo's stochastic nature. So low natural SIMD efficiency, low memory locality, challenges in reproducibility. But when we apply some GPU-specific techniques and remove some legacy CPU optimizations, we find that these issues we can mitigate, and we find that Monte Carlo actually maps very nicely to high bandwidth GPU architectures. All right, so with that, I can take any questions.
I have a question.
Sure.
For your data table from cross sections, have you ever thought of putting some of that in texture memory?
So I don't know, like you mean in like constant shared memory?
Yeah.
It turns out that the tables are very large. So we have hundreds of those tables, or maybe thousands of those tables, because like on a typical reactor simulation problem, we have maybe 300 or 400 nuclides we're tracking, and each of those has maybe 5 or 6 reaction channels that they have tabulated, and they're all on different grids and the data looks different.
Okay, so you have a region where most of the particles most of the time hit a certain region that would benefit from being in texture memory.
Unfortunately, the problem is that we don't have that kind of locality of like where, okay, most of the particles are going to be in this area. Like the particles tend to be in that space, in that logarithmic space, they tend to be sort of evenly distributed in that log space, in that log energy space. So we end up with, basically you have hundreds of megabytes or a few gigabytes of data that's being randomly accessed, at least if you're naive. The way we've improved it is by sorting the particles so then they all are hitting the same thing. Now, theoretically, what you're suggesting is there was some work in the past, I think it was called banded or macro bands or something, or banded Monte Carlo, where they would only run particles at a certain energy space, and so they would only be hitting a certain amount of kind of a slice of energy, and so you could just have only one set of data that you would load into texture memory. So that's conceivable that maybe you could try something like that. It could be beneficial, but it would introduce some complexity to the code.
Yeah, and maybe some imbalance.
Yeah.
Okay, thank you.
John, I have a question. You mentioned that getting rid of the software cache boosts the performance on GPU. How does that actually affect the CPU? I mean, is the software cache still beneficial today on CPU? Consider we have your code is now more SIMDized, and the CPU has larger cache.
Yeah, so let me see if I can get back to that slide. Maybe, hang on one second. Let me find that slide. I had some data here. All right, yeah. So the issue is basically the event-based mode where you can sort and you can have SIMD is slower on CPU. And so we can't really, it has to be in the context of history-based mode on CPU. And it turns out if we get rid of that cache, it does slow things down by about 25 or more %. So it is still a useful optimization on CPU. There could be some more work done, that maybe it's something that could be picked at of trying to improve event-based performance on CPU. There's a few ideas I have on that of theoretical ways. It gets kind of messy of how to, because you have to really have a good way of binding the different CPU threads together, and so you'd have to do a lot of thread synchronization, which gets a little bit painful on CPU. But maybe there's a way that you could improve the event-based performance. I will say that lots of other Monte Carlo groups have tried to get event-based to run on CPU and GPU, and they have found kind of similar things, where history-based tends to be optimal on CPU and event-based tends to be optimal on GPU.
Gotcha.
Hi, John. I have a few questions.
Sure.
You showed the optimized access kernel, and in the baseline there are there are loads and store, but in the optimized one, there are only loads. So so I'm confused where the stores are. The second question is when you compare AMD MI 100 with AMD MI 250 1 GCD, and is the performance improvement due to the memory bandwidth? I think the last question is for the 2 GCD, it is projected. Is there some issue with the hardware or the software, AMD software?
Yeah, so the different questions there. So the first one was basically we had stores here, and then all of a sudden on this slide we get rid of those stores. So did we need to be doing them? So the stores are storing into the cross-section cache, and if you get rid of that cache, then you no longer need to store it. The downside is now you have to do potentially more lookups. But when the lookups are so much faster, that it turns out the lookups are even faster than looking up out of the cache, just because they're so well organized. Whereas if you use a cache, your data is always going to be unique for each thread. And so basically it just goes by that because we've deleted that acceleration structure, we no longer have to store this data. Yeah. So then for the second question, which was on MI 200 versus MI 100. So yes, we believe that the speed up between MI 100 to MI 250X for 1 GCD follows pretty closely the amount of bandwidth difference. I believe there's about a 50% difference increase in bandwidth between MI 100 versus a single GCD of MI 250X. And so we get pretty similar to that, maybe 40 or 50%. So I think that's just due to bandwidth changes. And then in terms of why is it projected versus not a full value, that's just because these are very recent results and I haven't had a chance to compile with MPI on Crusher yet to get those results. But I have tested elsewhere on other GPUs, and our Monte Carlo we use MPI to run on multiple GCDs or multiple GPUs, and that sort of scaling is very efficient with Monte Carlo particle transport. So we don't expect to have many losses, if at all. It should be pretty efficient. So we're very confident in that projection.
I see, and we have to use MPI for 2 GCD, right? To run an application on 2 GCD, is that right?
Yes, that's right. Yeah, we have to use MPI. Yeah.
Oh, I see. Oh, thank you.
Yep. All right. Unless there's any more questions, I can pass it off to the next speaker. All right. I believe Scott McKinley will be speaking next.
All right. Okay. All right. Let's see. So I'm going to talk about Lawrence Livermore's movement into going on GPUs on Sierra. That's our big machine that we've gotten recently. Now, of course, we're working towards the next machine after that. So I'm going to be talking about 2 codes. The first is Mercury. It's basically just a general purpose code. It does neutrons, super thermal photons, and light ion charged particles, helium and hydrogen. It has relativistic physics. We can do fixed source problems and criticality problems. And we parallelize with replication and domain decomposition. It's written in C++. We have a Python user interface as well as embedded Python. And the whole goal in making this code was to make it sure it ran well on parallel machines. And it's about 20 years old and about 350,000 lines. IMP is our thermal photon code. So this is where you got tight coupling between X-rays and the material, where you have to do some kind of semi-implicit solves. And we had an older IMC capability. However, we did not want to port 2 codes to the GPU. So we decided, let's start doing code sharing between Mercury and this newly IMC code called IMP. And we did that, so therefore, by bringing Mercury up on GPUs, IMP came almost for free. Plus, IMP also got other features like restarts and graphics dumps and all sorts of other stuff that you can share between the 2 codes. And it's about 85 to 90% of the codes are shared. The codes is shared between the two. So that's helped us a lot in getting both codes going. And of course, the whole goal was we're moving to Sierra, and we're told, hey, lots of nodes. You got 40 CPUs and 4 GPUs per node, and 90% of the flops are going to be in the GPU, so you really need to go on the GPU. And there's also a 16 gigabyte limit per GPU, which comes into play later. So we started looking at this in 2017. By early 2018, we had kind of ported up our containers and memory allocation stuff to work on the GPU. We have a nuclear data library called MCGIDDI. It does nuclear data cross-section lookups, and it also does collision physics for us. It was C++ with virtual function calls and all sorts of stuff that do not work well going on GPU, but ported that. We managed to track our first neutron in April, our first thermal photon, and by June. By 2020, we realized we needed to do event-based, so we got that implemented. And here's a bunch of write-ups, anybody's interested. We start off, and we currently use managed memory. And the idea is we can quickly port our code over and let the code try to handle the memory eviction and all this other stuff as needed. And that way it can get us going and see what issues we have. So it kind of is true, but it also came with a lot of caveats that were not clear to us in the beginning. One is allocations of managed memory is very slow. We had to use a memory pool manager to help with that. Also with managed memory, you have to be careful with basically like function pointers. GPU function pointers and CPU ones are different. So we had some classes that had some polymorphism that would not work, so we kind of had to redesign them. It also does not have the standard template library, so we had to make our own versions of that. And also, as kind of pointed out earlier, Monte Carlo has just a lot of integer arithmetic, memory lookup, and Boolean decisions, and floating point operations tend not to be the limiting factor. We had to rewrite we had a threading loop. It was mostly for OpenMP on CPUs. So we're thinking tens of threads. And we would have one thread take over like what we call a chunk of particles. And you can think of it as like 10 to the 4th or 10 to the 6th particles based on how big you make a chunk. But each thread would get a chunk and work on it. And so that's not going to work on the GPU. So we rewrote it so each thread gets one particle. And so now we do a kernel launch on a chunk, do the work, and then in between kernel launches, we'll do MPI streaming. So this changed our MPI streaming as well from what we had before. But we're at the point now where the thin thread is as fast, as far as we can tell, as fast as our older fat thread model. So we're going to switch to it by default everywhere. Memory was an issue. Now that we had to start using atomics, we were creating bottlenecks and stuff. So we had to play around with replication and with atomics, and I'll go into a little bit more of that later. I think John really covered pretty well going from history-based to event-based, just as the way we had it. I mentioned we have a chunk, and our particle vault is basically a linked list of chunks. And you can think of a chunk as like a vector of particles. And so we'll call, based in our history-based model, we'll call a kernel on a chunk. All the particles are killed, or they make it to processing or processed part of the vault. And then when all processing is empty, then we're done with the cycle. So it was a pretty simple model, works very well on CPUs. But it was a huge kernel call. It was like 100,000 lines of code in this kernel. And it used max registers and lots of divergence. So we weren't making a lot of progress, even though IMP was doing pretty decent with this history-based approach. Switching to event-based, the big cost we end up winding up is all particles get copied per segment. So that was something that came out of this. but what we would do is figure out the distance to next event. And in this case, we're showing 3 events. And each event is just kind of an array of ints that point into the current chunk. And then later on, we do a kernel call over each event. And it goes into what we call a processing next. So there's the copy. Or if it hits census, it goes into processed. And then we just keep swapping out processing and processing next until it's empty. And at that point, we're done with the cycle. So early on, it was a good win for Mercury to go event-based. Imp was showing history-based was actually doing pretty decent and was beating it out event-based, which was very frustrating. So we tried to figure out what could be the issue. One idea was, well, maybe event-based is good at the beginning and history-based is good at the end. So we made the ability to switch partway through. Like when you get down to a certain number of particles, switch to history-based, but that didn't seem to help. The other idea was Imp has all the collisions are 1 particle in, 1 particle out. So there's a lot of the same particle staying in place. So we said, well, maybe it's the copying that's doing it. So we made a low copy mode, put a lot of effort in getting that working, and it actually slowed down the problem for some cases in the places that really should have sped it up. So that wasn't it. And during this time we're trying out these things, we noticed that Imp got faster for event-based. And we're not 100% sure why. Performance testing had fallen over during that time. So we weren't sure exactly when it happened, if it was better, so someone made a code change that did it, or some defaults got changed, or system update. So unfortunately, that was kind of lost, and we haven't gone back to figure that out because we're still trying to figure out why Imp does good for history-based in general. We also looked at other things. We tried to force lower register counts during compile just to get more occupancy. However, it never paid off. We tried that many times, and the compiler seems to know best, so just go with that. We have this idea of a compressed particle and an expanded particle. So the compressed particle, we call it a base particle, and it's the most memory efficient use you can get for it, and it's kind of what we send when we're doing Mpi communication or write restart dumps or store in the particle vault. And this expanded particle was what we used to track on the CPU just because you can throw cache space into it and it didn't matter. But now it does matter. So we've been trying to do more tracking with this base particle. But then some of the data that was needed, such as, what is the current facet we're crossing, or what was the current cross section lookup? Instead of storing that per particle, we decided to store that per chunk, which is a sidecar concept. So that helped us with some of our memory. We did a sort by cell, but it was only sorting particles to be in the same cell. It didn't sort by energy. So that's something I think we should probably go back and look at again based on what John just said. But it was very hit or miss. For the most part, it helped out history-based a lot, and it helped out Imp. But it did not help out Mercury that often unless we're doing history-based, and history-based was just not doing very good with us with Mercury. We also did mesh variables. The idea behind is like, if you're down at the cell level, your temperature, your density, your scalar flux tallies, whatever, store those in kind of a continuous array that's easy to access. And by doing that, we actually had certain things go up, like the pre-computing of cross sections went from 17% of the time down to 0.1%. I also tried the ability to just not pre-compute and not store some of this stuff, and that did speed up some problems. So we're trying to look at when does that speed up happen. I mean, it seems mostly, it was very non-intuitive to us, and so we're still looking at that, but it does seem to be in line with what John was seeing. We also varied the chunk size. We found on GPUs around 2 million particles was a good number to run a kernel launch on. And I think if you get bigger, you start hitting the 16 gigabyte limit. I think that's the issue there. If you go smaller, you're just not putting as much work out there at the same time. And so for CPU, it wasn't as big of an issue unless you worry more about memory. So we kind of default to like 10 to the 4th or 10 to the 5th particles for that. The tally replication, we found scalar flux. We didn't need to replicate atomics were fine, but common tallies, like we count number of segments or number of fissions. We found out 16 replicas actually seem to do pretty well for that. So we do 16 replicas with atomics, and things seem to speed up for that. We looked at asynchronous loops. We have one section where we're actually doing the events where we go asynchronous. However, when we're running efficiently, we pretty much fill up the GPU with one event, and it's only when that event tailing off does a next event start overlapping. And so we're seeing like a 5% speed up, but I think it helps out when we're running smaller problems. We looked at unity builds. That's basically when you concatenate all your source files into one file and compile that. And on some build systems that actually sped up the build, which is funny. But on running for GPUs, it tries to heavily optimize. And we did get a 25% speed up, just kind of looking at one problem on that. At the same time, we had someone else looking at link time optimization, and that came out with CUDA 11. And the idea is while you're linking all your compiled source files together, it can see the whole source or the whole code at that point, and the linker can try to do the optimizations then. And that's been tough because it's kind of a pretty new feature. But we've been getting 20 to 35% speed ups. And it doesn't mean we need to do unity build. It does add time to linking, but if you really want a fast code, this kind of pays off. Also early on, we weren't getting a huge speed up. So like if you're in the GPUs and you're seeing like, it's just as fast as running on the CPUs, we're like, okay, let's just run on both. And maybe we get a factor of 2 that way. So that was an early idea. And we've been playing around with that. So we do roughly see a speed up going CPU and GPU hybrid, but you really have to be careful not to hit a bad state, such as having, you got to make sure you balance out the number of particles sent to a CPU and to the GPU. Same thing for communication. GPU processors, with their MPI send, you make sure it communicates to another GPU and not a CPU, because you could overwhelm a single CPU core. So Ryan Blau's written a lot of papers about that. We talked about random numbers. We kind of just stuck with the 64-bit LCG. We had a library that had a lot of options, and users never ever picked a different option other than the default. So we're like, well, at this point, let's just go with the default, make an inline header file. So it's no longer a compiled library we link to, just a header. And then we expose it. So all this stuff gets inline. And it's kind of showed the main random number call we do, where every particle has its own seed and it calls this. We also have a spawn function. And I think basically it just swaps bytes. So you're just jumping around in this LCG pattern. So that allows for like daughter particles to show up. And we get pretty reproducible results in GPU and CPU. Where we start having problems is our Mpi communication. The order of operations comes out differently when we start pulling in MPI. So we start seeing differences as soon as we start running on more than one processor. But for the most part, the particles tend to do the same thing, and it's based on if we have feedback coming through or not. So it's kind of like a rough history of our speedups. We have 2 problems we've been looking at pretty consistently. For Mercury is a Godiva sphere and water, and we looked at alpha, and I'll show a little bit more about that later. For Imp, it's this crooked test pipe where heat's flowing down the pipe. And so I'm just going to compare running 36 cores on our CTS machine, which I'll talk about. I'll define what the CTS machine is on the next slide, versus 4 GPUs. So this is kind of our default comparison we can be looking at for speed ups. And when we first started out, Mercury was running half as fast, but Imp was actually running about 50% faster. And then by the next year, we've improved some, but by 2021, at that point, we had event-based, and that's where we got our biggest jump. And now we're around a 5x. So here's a little bit more about the Mercury and water problem, for the Godiva and water. It's an octet geometry, 27,000 zones. We run in 10 to the 8th particles, and we do an alpha calculation. So you have facet cross-sense collisions and census events. And so CTS1 is our kind of our standard CPU type computer we used to buy. It's the Intel Xenon, and it's got 36 cores, where the P9s are the CPUs on Sierra, and the V100s are the GPUs on it. So you can kind of see in the total time here at the bottom middle that going from CPU to CPU, CTS1 to Sierra, it slowed down a little bit. Other code sped up. It seemed to be based upon the code type, but it's not too bad. But we're seeing like a 5x speed up now. And we also look at the tracking time and the initialization to final time. So sometimes that has been the thing that's affected us. And the event-based is, only 50% faster. For the crooked pipe problem in IMP, it runs like 1,000 cycles, and it has like 10 to the 8th particles, and it's a 2D RZ geometry. So same compute things we're comparing against. It's going from CPU to CPU, from CTS1 to Sierra. It's like we slowed down 25%, which is kind of surprising. The event-based, we see about a 5x speed up. In history-based, we're seeing almost a 4x speed up. So we're still not sure why history-based is doing so well for IMP, given, we're just still trying to figure that out. So yeah, we've ported our codes over. We're seeing a 5x difference, but we're still working on stuff. We're still trying to figure stuff out. One is this compressed particle. We want to use that everywhere. That seems to be a win. So we're trying to get rid of this older data structure. We've several times played with structive array versus array of structs. So we have yet another commit where we're putting that in. We also, we're hitting the 16 gigabyte limit. So we're trying to now play around with the eviction ourselves, as opposed to let the computer do it. And we have one person interested in single precision calculations, so that might happen. But the big problem we have is the tools we have, they'll sometimes point out like, here's a bottleneck, but they don't really guide us into why it may be. And so that's been an ongoing issue. Plus we have a production code that we ported over as opposed to a new code. So we have a lot of features that have to get ported over with it, and making sure they all come over, I think, gives us a different experience than some other people did. We're currently looking at larger meshes and stuff. So we're playing around with ghost zones and seeing where that's efficient. Also per node, we have fewer MPI. Previously we'd have like 40 MPI per node, and now we have 4 if we have 4 GPUs. So we used to do a lot of load balancing by moving that work units around. And so now we have fewer work units. So that's impacted us, and we're trying to look around to see if we can do better there. So that's pretty much all I have, and I can take any questions.
Thank you, Scott. Really, really great talk. I think I'm going to keep it short here, so because we want to make sure we have time for our last speaker. So maybe we'll just do one question. Okay, well, if I guess I'll go ahead and ask then. So one thing I was interested in is if, as you have domain decomposition in both codes, right?
Right.
Has that introduced any complications for GPU that you weren't expecting? Did you end up having to use something like, CUDA-aware MPI or any advanced features, or was it a pretty natural, easy fix?
So far we let the CPU do the broadcasting, so that part worked. The big problem we've had is just the when we're running efficiently, we're kind of hitting the edge of memory, and so the randomness sometimes of streaming, or if you don't have the same amount of work coming through, we tend to blow some memory limits, and as soon as that happens, the code just grinds down to a halt.
Gotcha.
So that's been a big problem.
Gotcha. But so the strategy was you were getting great performance just moving the particles back to the host and then having the host handle that.
Right.
Gotcha. Cool. All right. Thank you so much, Scott. If we have time at the end, we can always loop back around, but I'd like to pass it off to our next speaker, Stephen Hamilton.
Yeah, can you see my slides?
Yep, looks great, Stephen.
Yep. So yeah, I'll try to be quick here. I know we're running a little bit short on time. So this is really kind of a stupid, simple study that I did recently. So I'm going to be talking about something a little bit different than the other talks. I'm not really talking about our Monte Carlo process itself. I'm going to be talking about some of the implications if we're doing a multiphysics calculation where one of your physics codes is Monte Carlo, and so it has some stochastic noise in it. And in particular, there's this method called Robbins-Monroe. It's an old method, goes back a long time. And I've been around a lot of discussions where people are arguing about whether or not you should use this method. And it felt like none of these arguments were being based on hard data. And so this is really just a study to convince myself whether or not this is an algorithm that we should be using in our multiphysics coupling. So this is coming out of the XSMR project. We're looking at doing coupled Monte Carlo neutron transport and thermal hydraulics, where the thermal hydraulics might involve CFD. In this study, it's not going to. But the essential physical coupling is our neutron transport describes how the neutrons distribute throughout a system, which tells us where fission events happens, which is a heat generation source term. The cross-section data that exists inside of that neutron transport calculation depends on the temperature of the material. So those are the two pieces in the neutron transport. On the thermal hydraulic side, the source term for our TH calculation is that heat generation rate from fission. And then we have the energy that is deposited is going to diffuse out through the solid regions. It's going to be carried away by the coolant in the system. So for now, we're only going to be talking about steady state coupling, but the basic ideas here would apply to transients and kinetics and things like that as well. If we were doing this problem in a deterministic sense, so if our neutron transport was a deterministic solver, we would have a variety of options available for solving these multi-physics systems. So we could do simple fixed point iteration, Picard, we can do Anderson acceleration, we could even do something like Newton's method. So some studies in the past have done JF and K on these coupled systems. But due to the stochastic noise in the Monte Carlo transport, we're really, for the most part, limited to just doing Picard iteration. So going over the notation that we use here are two different physics codes. So the neutron transport and the heat transfer are just going to be denoted by these two different script operators. So for the neutronic side, we're going to start with a temperature distribution. We use that to do a neutronics, and the output is a power distribution. Similarly, on the heat transfer side, we start with that power as a source term, and the result of the solve is a new temperature distribution. So if we want to write Picard iteration, all we do is we put iteration indices on these. So given a temperature distribution at iteration K, that gives us a new power. That most recent power goes into a heat transfer solve, gives us an updated temperature. That's our simple Picard iteration. So it's pretty well established that for a variety of different problems, if you do the vanilla Picard iteration, it might not converge. And this is true in a deterministic coupling sense. So there's feedback between the different physics codes that leads to oscillations that aren't damped out as you iterate. And so the standard universal approach is we're going to introduce a damping or relaxation factor, which here I'm going to call alpha. So we do our regular Picard iteration, and then we're going to add this little weighting factor, take a linear combination of the newest iterate and the one from the previous iteration. And if we pick that relaxation factor appropriately, then everything is nice and fine, and we've gotten rid of our instabilities. So the Robbins-Monroe algorithm, and this is a very old algorithm. I've got the citation down here. It goes back to 1951. So we're in that same time frame that John was talking about at the very beginning, when they were really just starting to look at stochastic algorithms. But the basic idea here is we're going to pick a relaxation factor that varies with iteration. And in particular, there are some constraints that have to be satisfied, but in practice, it almost always ends up being that the relaxation factor is 1 over the iteration number. And so that ends up looking something like these two terms here. And this is a little bit strange because what happens is as the iterations progress, the weighting factor applied to your newest component, the one that you've just computed, decreases and actually goes to 0. So as we progress, we're keeping more of the old solution, less of the new solution. If we take these equations and we kind of plug them in for the specific case of our coupling with the neutron transport, we carry it through. So you start with an initial temperature distribution. What you end up finding is that the power that is produced at some iteration k is actually an even weighting of all of the neutron transport solves that you have done so far. So after you've done 10 iterations, you're actually weighting each of the 10 neutronic solves that you've done are receiving an even weight to it, which seems strange if you're thinking about this in terms of a deterministic coupling. It feels weird because you have solutions that were done when your temperature was not converged are kind of being given the same weight as these new ones that presumably have a more converged distribution. So there's some pros and cons to this method, and the point of this study is just to evaluate whether or not this makes sense in practice. So the advantages are that you essentially get guaranteed convergence. So as long as you meet the criteria for the Robbins-Monroe relaxation factor, you're going to get guaranteed convergence. And it also has this property that the stochastic error in your final solution isn't limited by the noise in a single iteration. So it's not your uncertainty in a single neutronic solve that is dictating your overall convergence. So the disadvantages is just sort of this general feel that having the relaxation factor go to 0 doesn't feel right in a deterministic sense. So the method has a long memory. So if your nonlinear solution process has some errors from an initial guess, it may take a long time for those errors to be averaged out. And so we just want to do a pretty quick and dirty study to see, does this make sense for the types of problems that XSMR is interested in? So the numerical experiments here are using the Enrico code. This is something that was developed with ECP funding and XSMR. It allows us to toggle between using either Shift or OpenMC as our Monte Carlo solver. We can toggle between NEC, which is our CFD code, and a simpler internal subchannel solver for the thermal hydraulics. The test problem I'm going to use here is a pressurized water reactor fuel assembly. This is a full height commercial assembly, which is normally a more challenging problem for us. And in fact, this problem, if we used a deterministic coupling, this problem would be very unstable and would not converge without damping with a damping factor of maybe something like 0.5. So I actually picked this problem to be pretty challenging. In practice, it turned out not to be very difficult. So I need to go back to the drawing board a little bit and push this a little bit harder. Here's what the stability issues look like for this problem. So we can see that this plot here shows as a function of iteration. So as 4 consecutive iterations, you can see what the axial power distribution looks like. And if you look at it, it goes from something that's a little bit more peaked at a lower axial height to something that's peaked a little bit above. And this is the long-term behavior. It continues to oscillate between these two solutions. But I want to note that the magnitude of these oscillations is quite small on this problem. If we did this in a deterministic sense, the oscillations would be all over the map. They would be shifting from peaking down here somewhere to peaking way up at the top of the core, and it would really be bouncing around. So just there seems to be something about the Monte Carlo process that is already providing some kind of natural damping to this process. The negative on this is if you look at the magnitude of these oscillations, any one of these distributions actually looks physical. You can't really just look at that and say, oh, that's obviously wrong. Whereas if you had a deterministic solution that was oscillating wildly, you would know immediately that something was off. So looking at the behavior as we adjust the relaxation factors, you can see here, this is a function of Picard iteration, and the error here is actual error measured relative to a highly converged problem. So we ran something that had like 100 times as many particles as our most resolved other simulation. And the behavior here is pretty much the same with all of these. So you initially start to converge, and then you reach this stagnation point. So based on how many particles you're doing, your error is eventually going to flatline, and it doesn't matter how many additional iterations you do, you're not going to improve your solution anymore. You can see a little bit of strange behavior when alpha equals 1. So this is that undamped case. And what we're seeing here is there are some oscillations that cause the error to be a little bit larger in magnitude. But really, once your damping factor is around 0.8 or lower, everything is pretty sane here. So from this point on, I'm not going to focus much on the fixed damping parameters. We're just going to use this alpha equals 0.5, which is kind of what we would use in a deterministic coupling. So here's a case where we take that Picard with alpha equals 0.5, and we run it with a different number of particle histories for each iteration. And this is pretty much the behavior that we expect. So as we increase the number of particles, the multiphysics simulation converges, and then it eventually stagnates at some point. And that stagnation point decreases as you run more particles. And the stagnation point is exactly proportional to what we would expect from central limit theorem behavior. So if you look at, say, the blue curve versus the green curve, there's exactly an order of magnitude difference in the error where it stagnates, and we're running a factor of 100 particles. So it's exactly our central limit theorem behavior, 1 over square root of n. So then if we take that same problem and we run it with the Robbins-Monroe method, so this variable relaxation factor method, what we see is a little bit different behavior. So you have rapid convergence initially, and it then slows down, but it doesn't actually flatline. So it doesn't fully stagnate. And if you plot it against the 1 over square root of n behavior of central limit theorem, what we see is that we are getting exactly the expected 1 over square root of n behavior across iterations. So we don't get this in Picard. In Picard, we just flat stagnate, and there's a point in time where you're not doing any good anymore. Whereas with Robbins-Monroe, we're continuing to make progress towards our converged solution. And if we put these on top of each other, Picard and Robbins-Monroe, for the same particle count, we see that for the first couple of iterations, they'll follow the exact same trend. And then you see this stagnation in Picard, whereas Robbins-Monroe continues to follow this nice smooth convergence curve. And this is where it was really kind of unexpected behavior for us. I really thought because of the variable damping factor, because the damping factor becomes so small in Robbins-Monroe, I was expecting that we would see slower initial convergence, but then you would ultimately converge to a lower error. But what we see here is that Robbins-Monroe is always at least as good as Picard. So there is never a point in time when we're paying any penalty for doing this Robbins-Monroe. But it also gets you away from this stagnation point of Picard. So from what we're seeing right here, this is just a straight win. I think given that we're on short of on time, I'm going to skip over this discussion of figure of merit, but this is basically just a way of quantifying how good different solutions with different particle counts are in terms of reducing the error. And not surprisingly, Robbins-Monroe does very well in this respect. some of the caveats on the results that I've shown here, we're essentially assuming that the cost of the Monte Carlo transport is dominating your overall runtime. So in the case here, we're using a simple thermal hydraulic solver. This is a pretty good estimate. But if we're running a case where we're doing full CFD as the thermal hydraulic solver, there's going to be a different trade-off here. And we're going to want to perform fewer nonlinear iterations because a lot of that cost is going to be driven by the CFD, not necessarily just the Monte Carlo. And one final point I want to make, and this is kind of the implications for HPC calculations. One of the ways that a lot of teams over the years have addressed kind of this convergence issue with Picard iteration is by starting with a small number of particle histories and then ramping up the number of particle histories as the iterations progress. So you're getting better, lower error, a better resolution as your solution is more converged. And that kind of makes sense when you're running on a CPU, but that actually doesn't bias anything on the GPU. So our tracking rate depends very strongly on the number of particles that we have active at a particular point in time. And so that means if we run a calculation with a smaller number of particles for the first few iterations, we aren't actually reducing the runtime by the same factor that we would expect. So you're not getting the gain in runtime that you might expect by doing some cheap iterations for the first few iterations. And over on the right, I'm kind of showing the behavior that we typically see for particle tracking rate as a function of the number of active particles. So we generally have to get up to a pretty substantial number of particles to really get our peak tracking rate. And we tend to run right near this cusp here where we're getting close to our peak throughput. So that's basically all I've got. The initial results seem to indicate that this Robbins-Monroe algorithm, it's a really simple alternative to manually specifying relaxation factors. And for the most part, there doesn't seem to be a negative. We haven't seen a reason why you wouldn't just turn this on all the time. We do need to do some more testing on problems that have more challenging nonlinearities. So I'm thinking something like a problem with control rod movements where your power shape is changing dramatically over the course of a simulation. So that's something we'll be taking a look at pretty soon. And then kind of determining a way to identify an optimal run strategy when you have some non-trivial cost for both the Monte Carlo and your thermal hydraulic solve. So with that, I would be happy to take any questions.
Thanks so much, Stephen. That was great. Are there any questions from the audience? I'll kick it off with one. So it was very interesting that you said on the Picard iteration that it was converging, even though if you use like a diffusion or some sort of deterministic solver for the neutron side, it would you would see numerical instability and wild oscillations. Do you have any ideas on like what the mechanism for damping is in from stochastic algorithms?
I don't really, because we're running quite a few inactive cycles for each one of our Monte Carlo solves. So I mean, the initial thought is that the Monte Carlo solve isn't fully converged, because if you don't fully converge it, then it's reasonably well known that it kind of provides a bit of physical damping. So the MC21 guys have sort of shown this, that if you do your TH updates very frequently without fully converging the neutronics, then you end up not having any issues. And so it might be that even though I felt like I was running enough inactive cycles, maybe I really wasn't, pushing it hard enough to fully converge to the next solution. And so there's still a little bit of physical damping there.
Yeah, that's interesting. I've noticed it with random ray, which is a sort of a method of characteristics transport, that compared to deterministic Mach, it was more stable when for certain cross-section inputs, like the transport correction factor you apply to multi-group cross-sections can sometimes, if you're not careful, cause instabilities with deterministic. But for the same data set, the stochastic method was a little bit more stable. It wasn't perfect if you pushed it way out of line, but it was stable for a wider range. So it's interesting that maybe there's some.
I think the other thing there is with Monte Carlo, there's sort of different tolerances involved. When we're solving a deterministic problem, we might solve like the neutronic solve, we might get to a residual of 10 to the minus 6 or something like that. When you're doing Monte Carlo, that's never possible. You're talking 10 to the minus 2-ish is sort of the regime that we're in. So it might just be that the effective tolerance of Monte Carlo is not allowing you to fully capture that instability.
Gotcha. Yeah. And then I guess the other question I had was, do you expect different results? You said you wanted to pursue larger problems. Do you think, the question I had was, for the problems for the problems you've tested, what sorts of initial conditions were you using? And did you find much sensitivity? Like, were you using a cosine for temperature, or were you starting just everything was flat?
We're actually starting this. I was trying to start as far from the converged solution as possible to try to, see what happens. And so we start with a uniform temperature at the fluid inlet temperature. So for this one, I think it was 565 Kelvin, whereas you're hitting peak of, I don't remember, 1300, 1400 Kelvin or something at the center line in the fuel. So we're starting pretty far from our converged solution here.
Gotcha. So even with that, the Robbins-Monroe was still converging basically the same way as Picard, especially in the early part. It was still just as fast.
Exactly, and that was the surprise for me, was that there was no difference in them in those first few iterations. It just seems perfectly happy.
Very cool. Are there any other questions? All right, well, with that, I want to thank all our speakers for participating today. I thought it was really fun to hear about the different problems different app teams are facing, and the different challenges from nuts and bolts GPU stuff to more mathematical issues, and how it impacts the different fields. So just wanted to say thank you again to everyone. And with that, I will let everyone go. Thank you.
Thanks for organizing this, John.
Sure.